Hello and welcome to CS 4010. In this tutorial, we are going to study the vibration of a system, not a singular mass as we did in the last tutorial. An example is when you have sound propagates in air or water. Physically, you can consider that environment like a continuous environment. However, to apply the approximation, you must divide the environment into some discrete element like molecules or a bunch of molecules. If you have the mass of air is n and you try to divide it to n elements, so it will have each element has a mass of m, which equal to capitalize m divided on n. And it is different to what we have in the last tutorial where we have only one single mass attached to a spring. Here, each mass will have two springs connected to it and the adjacent neighbor. So therefore, you need to calculate the stiffness of these springs. If the environment has a total stiffness is K, then the springs between the masses will have the stiffness Kx equal to K times by n, where n is a number of elements. And certainly, the length of the spring equal to L divided by n, where n is a number of elements you divided to. Now, when we try to apply the approximation to this, we have to describe the problem in equation. And it is similar to what we have in the last tutorial. We have the inertial force, which is caused by the accelerations and the mass. And we have the elastic force, which comes from two attached springs. It's different to what we have in last time, because in last time we have only one spring, but here we have two springs. But the essence is similar. Now we just try to apply the approximation to this term and try to rearrange this to get the answer. Sometimes we can arrange it in terms of C, which is calculated from K, L, and M, and C is the velocity of the wave or the sound you have. Sometimes you can have it in form of the current number, which is calculated from the velocity and the delta t and the delta x you have for your simulations. And here is the final solutions for the approximations. You can calculate the positions of the element in the next time step t plus dt based on the current time step, the previous time step, and the position at the current time step of the adjacent masses. Now let's try to do a MATLAB example for this one. So in the first step, I need to set up the parameters for my simulation, like the mass of the environment, the stiffness of the environment, and the time of simulation, certainly. So my first parameter is Tf equal to, for example, I think it's just only 10 milliseconds. Because the sound propagates very quickly, I don't need to look at a long range of time. So this will be my final time of simulation. And my time step is about 10 minus 5. So this will be my time step. And to calculate the mass, I need the density first. So my rho equal to 1.225. This is the density of air in kilogram per cubic meter. And I assume that my sound propagates in a tube. So I have the constant mass. If a sound propagates in an open environment, so my mass will reduce by the propagations. So here I have the tube diameter is 0.01 meter. So this is my tube diameter. And my number of masses will be equal to 10. I just have 10 masses. And my L equal to 1. So I just have it propagates over 1 meter. And now I can calculate my mass of each element should be L over N times by pi times by the area of the tube could be d squared over 4 times by rho. So this will be just one mass. And it will be in kilogram. Now I have my stiffness. To know the stiffness, I need to know the sound. So which will be 300 meters per second. And I need my kx. I need a dx first to calculate this one. So my dx will equal to L over N. So this will be the step in x direction. And my kx equal to c squared over dx squared times by m. So it will be the stiffness of attached spring. This is a virtual spring attached to the mass I have. Yep, I think that is. Now I need to set up for the plot for illustration. So in here I will have my x range will be from dx to L minus dx on 2. Should be from dx on 2. So the mass will cover from 0 to dx. So therefore the position of this must be at dx on 2 at the center of the interval. And my step will be dx. And here will be my x range. And if I do this way, I will have a row vector. So therefore I should have this one should be transpose of this vector to get a column vector. Now for my y range, I have it always 0 because the sound propagates in x directions. So y equal to 0 up n by 1. So this will be my y values are always 0. And I need the dislocations of the element to show the vibration. So I need u equal to 0 up n. And I need a lot of time step. So therefore I need it scaling of tf over dt plus 1. So this will be the storage for this location. I need to set a timer. So time equal to 0. This timer will tell me which time step I'm on. So I set a timer for time step later. And I need a counter. As I told you in MATLAB, array start from 1, so I don't have it, the counter start from 0. So this will be my counter for calculation step. And I need to create a figure to plot out the data. To plot the initial one, I just use scatter. So I have h equal to scatter of x and y. So I plot equilibrium. you can just remove the h equal to scatter, but I want to replot again and again later, so I want to remove the previous graphic, so I assign this to a variable. So now I just try to do x limited will be from 0 to L. So I will focus on this range. So the given range. And for example, x label, I have this one should be x in meter, for example, like that. And certainly I want to hold on. If I don't hold on, it's okay, but it will erase my xlim, so therefore I want to hold it on. And now I start my main loop. So as normal, in the main loop we use a while condition, so until the time is larger than the final time. And in this first step, I am to plot what I have calculated. So I delete h. So I remove the previous graph. And then I plot what I just calculated. So h equal to scatter up x plus u, where u is this location's array, but I need it in the current step. So therefore, I take everything from the first index, but for the second index, I just go for t only. And y, which is always 0, and 25, which is the size of scatter, and marker h color should be blue, for example, and my marker face color should be red to be in contrast. So I just plot the current position. Now I need to make a timestamp to tell the reader which time I am at. So I use title to get this one. It will be an array of, the first will be a string, time equal to, and then after that will be the time, but I have to convert it, so num to string, the time. This way I will convert the time variable to a string to be plotted, and certainly I add the second as a unit of my time. So here is my timestamp. And I pause for a DT as I did in the last time for viewing. So pause to see movement. Now, after I plotted the current step, I need to move to the next step. So for the next calculation step, I get t equal to t plus 1. Next calculation step. And for that, I need to reset the boundary condition u at 1t equal to 0.05 time by sine up time by 100. So this way, the first element in the range at the current time will be set to a specific positions by a sine function. This way, the first element will invoke the vibrations. It will start the vibration, and the vibration will be transported to the other end of the mask. So this one will be reset the boundary condition. And now I can calculate the position of other masses based on the mass I store in U and the new positions of the first element. So for I equal to 2 to n. So I will calculate for everything. Hang on, I don't need the last one. My u of I at the next step will equal to, now I use the main equation, the main approximation I have over here, will equal to 2 times by u it minus u I at t minus 1, that's the previous positions, plus kx times by dt square over m, and times by, now in the bracket we have this term should be u at I minus 1 t minus 2 times by u it plus u I plus 1 t. Okay. So here I just calculate the next position. And that is for the for loop. After all, I just need to move my time step. So time equal to time plus dt for the loop condition. And this also the preparation for the next time step. Yep. I have no mistakes, and you can see here is the first element that vibrates by a sine functions, and when this move, it also make a elastic force on the spring that attached between two adjacent elements, and then the vibration is transported from one side to another side. Let's see again. And this element is the end of the mass of the environment, so therefore this one doesn't move, only this one moves. And you can see the sound has been transported from the other end and then reflect back. In the next tutorial, we are going to study the vibration of a system with damping coefficient. Thank you very much, and see you in the next tutorial.